Hello and welcome students. We are going to see the last topic in our chapter, electric charges and fields. Okay, so we'll start off with continuous charge distribution and we will see Gauss law. Okay, so Gauss law and its applications are the last topic. Okay, so what do you mean by continuous charge distribution and why should we study about continuous charge distribution? Till now, if you look at our chapter, electric charges and fields, we have discussed about point charges and about dipoles. So point charges and dipoles, if you take, they are actually charges which are present at a single point, dipoles present at two different points, but what happens is the electric field due to them will be very much different. Okay, so for point charges and for dipoles, the electric field as we move away from the point decreases, and as we move towards the point, the electric field becomes very large. It might even become infinite. Okay, so as we go very close to a charge, the electric field can even be infinite. Now, what about electric fields due to charged conductors? Conductors are metals which conduct electricity. They have many charges inside them. Some conductors have charges in static condition also. So for such static charges, how do we calculate the electric field? In a conductor, if you take, or a section of a conductor, the amount of charges present would be huge. They would be in billions and billions, right? So therefore, for those charges, how do we calculate the electric field? For that, we have to discuss about continuous charge distribution. Okay, so the meaning of continuous charge distribution is that the charge is distributed along the length of a conductor, or along the area of a particular metal sheet, or along the volume of a particular metal, right? So therefore, when the charge is distributed along the surface, we can in general take that the charge distribution is uniform. So under uniform charge distribution, we are going to introduce a few terms. Okay, so let us take a conductor for example. On the surface of a conductor, if you take a small area over here, let us say the area is del S. For this area, we can calculate the number of charges present here and we can find out what is the charge density. Okay, so the charge density for this particular region, we can call it as surface charge density. Surface charge density is given by the symbol sigma and it is the charge present in that region. We can call it as del Q amount of charge present here in an area of del S. Okay, so surface charge density is sigma, which is nothing but charge per unit area. Okay, so the unit for that will be coulomb per meter square. Okay, charge per unit area. So this is for a surface where charges are present, right? If there is a line where lots of charges are present, either positive or negative, we can take a length along the line called as del L, and for that del L, if let us say there are del Q amount of charges present here, then we can introduce a term called linear charge density. Linear charge density we can represent as lambda. It will be del Q divided by del L. Okay, so the charge per unit length is called linear charge density and its unit will be coulomb per meter. Okay, so coulomb divided by meter, coulomb per meter. So this is linear charge density. Now if there is a three-dimensional object which has volume, for a small volume in that object of del V, if let us say del Q amount of charge is present there, we can even introduce a term called volume charge density. And volume charge density we can represent as rho. It will be equal to del Q by del V, the charge per unit volume. Okay, so the unit for that will be coulomb per meter cube. Okay, so these three terms, surface charge density, linear charge density and volume charge density, come under surface continuous charge distribution, assuming that the charges in these areas or along the length or in a volume are uniformly distributed. Now let us see how to calculate the electric field due to such continuous charge distribution. Okay, so let us take the case of an object which has a particular volume. Okay, so we are going to take a small volume in that called as del V, and let us say del Q amount of charge is present in this region. Okay, so the volume charge density of this will become rho. The volume charge density will become rho, considering that all the charges are uniformly distributed in that object. Now let us take a point P at a distance of r from this volume, okay, from del V. Now how do we calculate the electric field? Electric field due to del V at point P will be del E. Okay, the electric field can be calculated using this usual formula, 1 by 4 pi epsilon naught q by r square. Okay, so 1 by 4 pi epsilon naught. Instead of charge, we are going to take in terms of volume charge density. Okay, so therefore del V will multiply to the other side. We will have it as rho del V. So del Q will be rho del V. Let me write it here. Del Q will be rho del V from this equation. So therefore we can substitute as rho del V divided by r square. Okay, where r is the distance between this volume and the center of this volume and point P. Now how do we calculate the total electric field? The total electric field can be taken as a summation. 1 by 4 pi epsilon naught will be a constant. Summation of all the del V volumes present in this volume, which make up the total volume of V. Okay, which make up the total volume of this object. So the electric field due to this object, whole object at point P, can be calculated as a summation of all the volumes, of all small volumes, and here we'll have rho into del V divided by r square. When you take a summation of rho del V, we'll get the total volume, right? So volume charge density multiplied by total volume divided by r square we'll have in the equation for finding out what is the electric field. Okay, so using this we are going to see what is Gauss law next. So let us start with Gauss law. So to prove Gauss law, we are going to take a point charge plus q, right, and we are going to take a sphere around it, okay, at a distance of r, which has a radius of r, right. So we are going to take a sphere around it. Now in that sphere, let us take a small surface del S, okay, an infinitesimally small surface del S. Let us take a small area, and through that area or through that surface the electric field we can draw. So this is the direction of electric field. Now Gauss law is a law which is going to tell us about the electric flux. Okay, so therefore using this we are going to calculate what is the electric flux through this area del S due to the charge plus q, right. So the flux we can calculate as del phi, because it is through area del S. Let us calculate the flux as del phi. Now flux will be equal to E vector dot del S vector. Okay, the dot product of these two, dot product of electric field and the surface area. Okay, so how will we write that? Electric field, let us substitute the expression. It will be q by 4 pi epsilon naught r square, and del S vector, we can just write the magnitude of del S vector as del S. Okay, so just the magnitudes we have taken, not the directions. So magnitudes alone, if you write, we have q by 4 pi epsilon naught r square into del S. So this is the flux coming out through this surface. Now how do we calculate the total flux coming out of the sphere due to the charge plus q? How do we calculate that? The total flux will be a summation of all such small surfaces del S, which will constitute the total surface. Okay, and we can take it as summation of del phi. Okay, the flux that we have found here, right? So when you take a summation, what will we get? We have q by 4 pi epsilon naught r square as constants, and we have summation of all such small surfaces del S multiplied by summation of this. Okay, so summation of del S will give us what? The total surface area. What is the total surface area of the sphere? The total surface area of the sphere we can write as S, and for a sphere it is 4 pi r square. Okay, the surface area of a sphere is 4 pi r square. So total flux coming out of this surface 4 pi r square will be q by 4 pi epsilon naught into r square into the total surface area 4 pi r square. Now 4 pi r square and 4 pi r square will get cancelled, and we get flux equal to q by epsilon naught. So this expression is called as Gauss's law. Okay, it was found by a scientist called Gauss, and it is another form of Coulomb's law. Okay, so Gauss law is another form of Coulomb's law. It is dependent on inverse square law also, right? So therefore it has been derived from Coulomb's law. So therefore Gauss law is very, very important in electrostatics, and it is very useful to calculate the electric flux or electric field due to continuous charge distributions. Okay, that is what we will be seeing next. Applications of Gauss law we'll see, right? So how do we state Gauss law using this expression? The expression is phi equal to q by epsilon naught. So we can state that the total flux coming out of a closed surface, is equal to 1 by epsilon naught times the charge enclosed. Okay, so we can write this as total flux equal to 1 by epsilon naught times the charge enclosed. Okay, so the charge that we are writing here, Q, is the charge enclosed by this closed surface, right? So this is the statement for Gauss law. The total flux coming out of an enclosed surface is equal to 1 by epsilon naught times the charge enclosed by that surface. Okay, so another example we are going to see to prove Gauss law, to apply Gauss law, right? So let us take a cylindrical surface, okay, a hollow cylindrical surface placed in an uniform electric field. The uniform electric field's direction is towards the right. Okay, so the electric field lines will be passing through the surface like this. Okay, right? So we have taken a cylindrical surface and electric field lines are passing through like this. Okay, now what will be the total flux from that closed surface? What is the total flux coming out of the closed surface? How do we calculate? If you apply Gauss law, it is very, very simple. The charge is 0. Which charge is 0? The charge enclosed by this surface is 0. Therefore, total flux will be 0, right? So, according to Gauss law, it is very easy to evaluate. The charge enclosed is 0, and therefore we can write that flux is equal to 0. The flux coming out of the closed surface is 0. Okay, here you can notice one thing. If you don't apply Gauss law and you want to evaluate, how do you do that? Okay, so here you can notice one thing. The flux lines are going in for this surface and flux lines are coming out of this surface. Okay, so if you take this as surface 1 and this as surface 2, for surface 1, what can we write? The flux that is going inside is generally taken as negative. So therefore, we will write it as electric field multiplied by area. Let us take the area of this area of cross section as A. So here the flux will be minus EA because the flux lines are going in. Over here the flux phi 2 for the second surface will be plus EA because the flux lines are coming out. Since area of cross section is the same on both sides and it's a uniform electric field, phi 1 and phi 2 will be having the same magnitude, but phi 2 will be positive and phi 1 will be negative. Now can you calculate the total flux? Total flux will be phi 1 plus phi 2, which is equal to minus EA plus EA equal to 0. That is what we saw in Gauss law also, right? So using Gauss law, we have found out the flux very easily just by applying a very simple concept. The charge enclosed is 0, therefore total flux coming out will obviously be 0, right? So the same we have proved using the normal method of finding out the total flux. So this proves Gauss law. Okay, so let us see again what is the statement for Gauss law. The total flux coming out of an enclosed surface, a completely enclosed surface, will be equal to 1 by epsilon naught times the charge enclosed by it. Certain important points we have to note down about Gauss's law. Okay, so the first point is about the surface that we are taking as the enclosed surface. Okay, so Gauss law is true for any closed surface, and it can be of any shape or size. So irrespective of shape or size, the surface must be completely closed. That's it. So it can apply for any closed surface. Okay, so such a closed surface is actually called as a Gaussian surface, which we are going to see in this point. Okay, so the charge that we have taken in Gauss law, we have phi equal to q by epsilon, right? So the charge q is actually the charge enclosed by the Gaussian surface. So only those charges inside the Gaussian surface are to be taken on the right hand side of the equation as charge q. Okay, so sum of all the charges that are enclosed, there might be many charges inside the enclosed surface also, inside the Gaussian surface. So sum of all those charges together is called as the charge enclosed. So the charges may be anywhere inside the surface. It is not necessary that the charge should be at the center or on the surface or anything like that. The charges might be anywhere inside the surface. Gauss law would apply. Only the sum of all the charges we have to take, right? Then, if this is a Gaussian surface and we have charges plus q1 and plus q2 inside and plus q3 inside, plus q3 outside, the charge enclosed would mean only q1 and q2, not q3. Okay, so when you take the charge q, it represents only the sum of q1 and q2 for this example, right? So it includes only q1 and q2. But when you calculate the electric field crossing this particular surface, okay, the electric field due to all these charges will be actually because of q1, q2 and q3. Okay, so the electric field in this region will be due to all the charges. But when we apply Gauss law, we apply only for the charges that are enclosed. Do you understand? So the resultant electric field will be due to all the three charges. So calculation of electric field will be due to all the charges. But when you represent Gauss law, phi equal to q by epsilon naught, when you take q in that equation would represent only q1 and q2. Okay. Then what about a Gaussian surface? A Gaussian surface is an imaginary surface. All of you should remember. Gaussian surface is an imaginary surface that we are taking to apply Gauss law. Okay. And to find out the flux and obviously electric field also in certain cases. So Gaussian surface is generally drawn free of charges. Okay, it is never drawn through a particular charge, through a point charge. Okay, that would lead to some difficulties. Gaussian surface can be drawn outside the charges or excluding a particular charge, but it should never be drawn through a point charge. Okay, but Gaussian surfaces can be taken passing through any continuous charge distribution. Okay, that will not be a problem. But for point charges, the Gaussian surface when you draw, it should not pass through the point charges. It should not be taken through the point charges. Okay. Then we have the application of Gauss law. Easier calculation of electric field is the main application for Gauss law. So it can be used for easier calculation of electric field provided that the system is symmetrical. So for symmetrical systems, for continuous charge distributions, we can use Gauss law for easy calculation of the net electric field. Then any violation of Gauss law will mean that we are departing from inverse square law. The meaning is that we are moving away from inverse square law, and we know that Gauss law is dependent on Coulomb's law. It has been derived from Coulomb's law, and it is also dependent on the inverse square law. So we cannot move away from Gauss law. That means we cannot apply in such a way that it proves to be wrong. Okay, so therefore we should not violate Gauss law. If a violation of Gauss law will mean also a violation of inverse square law. Next, let us see the applications of Gauss law. The first application is an infinitely long, straight, uniformly charged wire. Okay, so for this we are going to find out what will be the electric field at any point near to it. Okay, right. So an infinitely long, straight, uniformly charged wire can be represented like this. It will be cylindrical in shape. Generally, we take wires to be cylindrical in shape. Okay, and it is uniformly charged by positive charges as I have represented here. Right. So it is an infinite long wire, so it extends on both sides infinitely. So how do we consider or apply Gauss law over here? Now for Gauss law, we have to first draw a Gaussian surface, correct? We have to first consider a Gaussian surface. As I told you, the wire is cylindrical in shape, so the Gaussian surface that we are going to take is also cylindrical in shape. So how do we take the Gaussian surface? First, the point P we have to take. At the point P is the point where we have to find the electric field. So at point P, let us mark point P over here and take the distance from the wire to be the R, the value R. Okay. So with respect to point P only, we are drawing the Gaussian surface. So the Gaussian surface is a cylindrical surface whose this is the cross-sectional area of the cylindrical surface, and the radius of the cross-sectional area will be the distance of the point P from the wire. Okay, so the Gaussian surface is taken in such a way that it passes through the point P at which we want to find the electric field. So the electric field due to all these charges will be pointing in this direction. Okay, it will be pointing horizontally, it will be pointing perpendicular to the infinite long wire. How is that? Charges over here, okay, they will direct an electric field in the opposite direction, in this direction. Charges over here will direct the electric field in this direction, but when you take a vector sum of all those electric fields, they will point only horizontally. The vertical components will get cancelled out. The vertical components of the electric field will get cancelled out. So therefore, even if you take extreme charges, charges which are not at the same level at this point P, they will cancel out their vertical components of electric field, only the horizontal component will remain. So when you take point P anywhere surrounding this near this wire, infinite long wire, the electric field will always be pointing horizontally or perpendicular to the wire. Okay, right, now that we have cleared that, we are going to apply Gauss's law. So Gaussian surface we have taken, the length of the Gaussian surface we have taken as L, right? We are going to apply Gauss's law. Now what is Gauss law? Gauss's law is given as phi equal to Q by epsilon naught. Now phi can be written as electric field multiplied by the surface. Okay, so the flux coming out of this side surface we have to take. Okay, the side surface or curved surface of the Gaussian surface, Gaussian cylindrical surface that we have taken, we have to write over here. So flux will be equal to electric field multiplied by the curved surface area, which is 2 pi RL. Okay, curved surface area for a cylinder is 2 pi RL. That will be the flux coming out. And what about the charge enclosed? The charge enclosed will be the total amount of charge present from here till here, from the top of the cylindrical Gaussian surface till the bottom of the cylindrical Gaussian surface. So that will be the total amount of charge for a length of L. Okay, so we can take it as line charge density, linear charge density multiplied by the length L. Okay, now if you substitute this in the Gauss law, what do we get? E into 2 pi RL will be equal to lambda L divided by epsilon naught. So L will get cancelled. We can take 2 pi R to the other side. So we have lambda divided by 2 pi epsilon naught R. So this is our expression for electric field due to infinitely long straight uniformly charged wire at any point near it. Okay, so therefore electric field is lambda by 2 pi epsilon naught R. If you take the unit vector n cap in the direction of electric field, you can even write this as a vector as lambda by 2 pi R epsilon naught n cap. N cap is the unit vector in this direction. Okay. Next, let us see uniformly charged infinite plane sheet. We are going to find out the electric field due to a uniformly charged infinite plane sheet. Here we saw an infinite wire. This is an infinite plane sheet. Okay. So electric field at a point P we are going to find, that is at some distance from the plane sheet. Okay. So actually the formula it does not depend upon the distance from the plane sheet. The electric field at any distance from the plane sheet is going to be same because it is an infinite plane sheet, right? But the direction of electric field, as we justified in the previous case, it will be perpendicular to this surface. It will be perpendicular to the surface of the plane sheet, right? Now how do we apply Gauss law over here? We know that Gauss law is phi equal to Q by epsilon naught. How do we calculate the flux over here? The flux will be coming out on both sides, okay, from here and from here. So it will be, the total flux will be flux 1, that is flux from the right hand side, flux from the left hand side. Phi 1 will be E into area. Okay, so the area of this surface is A, so we have taken as E into A. Phi 2 also will be E into A, because on both sides the flux lines are coming out, both will be positive. Also one more thing I forgot to tell you, the Gaussian surface that we have taken here is a cylindrical surface. You can even take it as a cuboidal surface as given in your textbook. It will provide the same result only. Okay, so we have taken a cylindrical surface. The cylindrical surface passes through the plane sheet. Okay, so the area of the cylindrical surface, cross-sectional area, is A. The same cross-sectional area A will be applied on the plane sheet also over here, and in this area whatever charges are present, only those charges we have to take. Okay, so according to Gauss law we have to find the charge enclosed, correct? So the charge enclosed will be nothing but the charge in this region. Okay, so we can take surface charge density sigma multiplied by the area, sigma into area A, right? So this is the charge enclosed. Total flux phi1 plus phi2 will give us EA plus EA, which is nothing but 2EA. Total flux will be 2EA. Now if you apply that in Gauss law, on the left hand side we will have the flux, which is 2EA. On the right hand side we have the charge enclosed sigma into A divided by epsilon naught. Now you can see that area on both sides gets cancelled, and electric field you get as sigma by 2 epsilon naught. If you take it as a vector quantity, you can even write n cap. N cap is the unit vector along the direction of electric field. So on the right hand side this will be n cap, on the left hand side this direction will be n cap. Okay, so this is the expression for electric field due to an infinite plane sheet. Both these expressions are very important. They will be very useful for your problems. The last application that we are going to see for Gauss law is a uniformly charged thin spherical shell. Okay, so this is the spherical shell that we have taken. The charges are present on its surface. Okay, so all the charges are present on its surface and it is uniformly charged. Okay, so and we are going to find out what is the electric field. The first thing is electric field outside the shell. So let us take a point P which is outside the shell at a distance of small r from the center. The radius of the shell is capital R. So obviously in this case small r will be greater than capital R. So at point P this will be the direction of electric field away from the center. Okay, along the radius away from the center. Now how do we apply Gauss law? Gauss law is phi equal to q by epsilon naught. The flux coming out of this charged shell, coming out of the Gaussian surface, will be E into 4 pi r square. 4 pi r square is the surface area of the Gaussian surface. Okay, so E into 4 pi r square gives us the flux coming out of the Gaussian surface, and we'll have q by epsilon naught, right? So q is nothing but sigma into 4 pi r square. Q is the charge that is present on the spherical shell. It will be surface charge density multiplied by the surface area of the shell. So surface area of the spherical shell is 4 pi into its radius square. Okay, so sigma into 4 pi r square divided by epsilon naught we have. So here 4 pi and 4 pi will get cancelled, and electric field will be sigma r square by epsilon naught into small r square. And instead of sigma instead of sigma, if you are going to substitute in terms of charge q equal to 4 pi capital R square into sigma, if you are going to substitute, we can even get the expression for electric field as q by 4 pi epsilon naught r square. And if you are going to include the unit vector r cap over here, this will also become a vector. Okay, so it can even be a vector quantity if you include the unit vector r cap. Okay, what about the electric field on the surface? The electric field on the surface of the spherical shell, that means if point P is present over here on the surface of the spherical shell, the value of R will be equal to capital R. The value of small r will become equal to the capital R, equal to the radius, and the electric field will be sigma by epsilon naught into r cap. Okay, so r square and r square will get cancelled because they will become same, and electric field will be sigma by epsilon naught. So for a uniformly charged spherical shell, thin spherical shell, on the surface the electric field is sigma by epsilon naught, and r cap is the unit vector in that direction. Finally, we come to the electric field inside the shell. This is often asked as a 1 mark question. What is the electric field inside the uniformly charged thin spherical shell? The electric field inside the shell is 0. Why? Because the charge enclosed within this Gaussian surface will be 0. Correct? So if you take a point P which is inside the charged spherical shell, this is the charged spherical shell. Okay, so the charges are present on its surface. Now if the point P lies inside the shell, then you will take the Gaussian surface with respect to point P as a spherical Gaussian surface we will take, right? So what will be the radius of Gaussian surface? It will be lesser than the radius of the sphere, correct? And what will be the charge enclosed? All the charges are found outside the Gaussian surface. No charges are inside. So therefore, Q equal to 0 and E into 4 pi r square, we'll get it equal to 0. Therefore, electric field is 0 inside a charged spherical shell. Okay, very important point. So you have to remember that. With this, we are completing our chapter. Okay, all the theory part in our chapter we have completed. Please prepare all the derivations well and learn all the concepts and definitions. Be thorough with them. Okay, a few examples are left out which we will cover in our next session, and the exercise questions also we'll discuss. Right, so keep preparing, study well. All the best and thank you.